My name is Brad Gibbs. I'm the Business Development Manager for International Dioxcide, an ERCO worldwide company. We hope you enjoy this session today. We hope to provide valuable insights into chlorine dioxide and enhance your knowledge in the subject. We have a great panel of speakers today. Leading off, we'll have Scott Glenn. He's a senior chemist. He'll review the chlorine dioxide properties and its historical use in drinking water. Next, we'll have Dr. Zach Lee, a senior process engineer. He will elaborate on how chlorine dioxide can improve unit operations to deliver exceptional water quality. And last, we'll have Dr. Alan Burke. Alan is a chemical engineer, and he will cover the regulatory compliance and chlorine dioxide generation methods. Each presenter is employed by International Dioxide, an ERCO worldwide company. For over 75 years, IDI has focused on delivering to the market effective precursor chemistries to chlorine dioxide while also providing generation equipment as an option. But with that, I'll turn it over to Scott Glenn. Scott.
Thank you, Brad, for the introduction. I'm Scott Glenn, and I will be presenting a high-level introduction to chlorine dioxide and its use in municipal drinking water. My colleagues, Drs. Lee and Burke, will provide a more in-depth discussion on the topic. As you can see, there are many markets and applications where chlorine dioxide is used. For today's discussion, we will focus on its use in municipal drinking water. Within the drinking water application, there are several areas where chlorine dioxide is used, from disinfection of various types of organisms to oxidation of compounds that can leave stains on fixtures and clothing, to leaving a bad taste or odor in the water. The use of chlorine dioxide can aid and enhance many water processes such as coagulation, sedimentation and filtration, cleaning of the system by reducing and preventing mollusks and biofilm, all of which can lead to a reduced demand for residual disinfectant and improve overall water quality. We will discuss these uses later in the webinar. Chlorine dioxide is a chemical that was discovered over 200 years ago and only started being used commercially about 80 years ago. While chlorine dioxide has chlorine in its name and structure, it is very different than chlorine. Chlorine dioxide is a gas and is predominantly generated in water where it remains as a gas and is applied as a solution in most applications. Unlike chlorine, the gaseous form of chlorine dioxide cannot be compressed and shipped in cylinders, requiring it to be generated on site. Chlorine dioxide solutions are typically a light yellow-green color, which increases in intensity and color as the concentration increases. Chlorine dioxide is a free radical, which simply means that it has an unpaired electron and wants to react with something that gives up an electron in a true oxidation reduction process. Therefore, chlorine dioxide functions as a highly selective oxidant when it reacts, which can lead to a much lower required dose to achieve the desired effect. Because chlorine dioxide reacts only via an oxidation process, it does not form chlorinated organics, trihalomethanes, or haloacetic acids. In fact, chlorine dioxide reduces the formation of these THM and HAA precursors. On the other hand, chlorine, which can react via 3 different methods, oxidation, addition, and substitution reactions, form halogenated organics, including the THMs and HAAs. Chlorine dioxide is a powerful biocide, one of 4 approved by the EPA for use in potable water disinfection. Because chlorine dioxide remains as a gas dissolved in water, it remains effective over a wide pH range, unlike chlorine and bromine, which become weaker disinfectants as pH increases. Chlorine dioxide is a broad-spectrum biocide, as it is effective against bacteria, viruses, algae, biofilms, and other organisms. Due to the way chlorine dioxide reacts with organisms, it oxidizes the basic cell structure and shuts down its metabolism. It is theorized organisms cannot develop an immunity to it, unlike other disinfectants. In most applications, a lower dose of chlorine dioxide is required to achieve disinfection or oxidation, which translate into being less corrosive than other halogenated products. In the end, chlorine dioxide and its byproducts ultimately degrade into salt. Chlorine dioxide was first used in the US in 1944 in Niagara Falls, New York, for taste and odor issues. Use of chlorine dioxide had a slow growth over the next 30 or so years until the 1970s when trihalomethanes were discovered in drinking water. Health concerns related to those THMs resulted in an increase in the use of chlorine dioxide, with hundreds of water plants using it by the 1990s. Due to regulatory pressures in the 1990s and 2000s around the disinfection byproducts related to chlorination, the use of chlorine dioxide increased to over 1,000 facilities in the US and even more globally. With its growing use in disinfecting drinking water, other industries took notice and started using it as an effective alternative to chlorine and other disinfectants. As mentioned previously, there are many locations that chlorine dioxide can be applied to in the water treatment process. In the US, chlorine dioxide is predominantly used for pre-oxidation and primary disinfection, and in a limited but growing market, the supplemental water treatment process. In the pre-oxidation zone, such as the raw water intake to the sedimentation process, where chlorine dioxide is used to oxidize iron, manganese, organic precursors that help form the THMs and HAAs, and even for early CT credit. In the primary disinfection zone, at the filters and clear well for CT credits and a reduction of chlorine dose leading to THMs and HAAs. In the secondary disinfection zone, the water enters the distribution system where a chlorine dioxide residual can help clean up the distribution system, resulting in a longer lasting residual due to biofilm reduction and nitrification control. It should be noted that in the US, chlorine dioxide is generally not added to the distribution zone system, but is carried over from the primary disinfection zone. In the supplemental or secondary water treatment zone, such as in industrial, hospitals, and other small applications for potable and processed water disinfection. That concludes my portion of the presentation. I will now turn over the rest of the following slides to Dr. Lee to discuss in more detail. Thank you.
Thank you, Scott, for the overview. Next few slides, I would like to go through with you some more detail about a few applications of chlorine dioxide in drinking water treatment system. Many US utilities using chlorine dioxide as a pre-oxidant to remove iron and manganese from the source waters. Iron and manganese can either be present all year round in some groundwater or be present seasonally in source water contamination. Increased in iron and manganese content can cause rusty metal taste and odor and cause color in water. Iron and manganese is regulated by secondary MCL. Iron is regulated at 0.3 ppm. Manganese is regulated at 0.05 ppm. US EPA also has a health advisory level for manganese at 0.3 ppm. Different approaches were taken to deal with the iron and manganese issue. Potassium permanganate, for example, is used to oxidize iron and manganese. Ozone is also used. Overshot from permanganate and ozonation may redissolve manganese as permanganate iron in water. This can cause pink water issue in tap water. Aeration and chlorination, on the other hand, is a very slow reaction and usually takes days to hours to complete the oxidation. Incomplete oxidation of manganese and iron can form colloidal forms of iron and manganese, which becomes very difficult to remove from the system. And the breakthrough and carry over of iron and manganese tend to cause filter clog and filter effluent turbidity issue, and they can also cause the downstream distribution system, valve and pipeline clog or precipitation. Chlorine dioxide provides better control of iron and manganese than any other oxidants. An oxidation of iron and manganese, as shown in these equations on the screen, convert dissolved form of iron and manganese into solid form of iron and manganate. This is combined with conventional solid liquid separation can usually provide very good removal of both iron and manganese. Disinfection by chlorine dioxide and chlorite residual helps to kill iron and manganese bacteria, which prevent further downstream catch and release of iron and manganese particles in distribution system. Besides iron and manganese oxidation and removal, chlorine dioxide treatment can also control many other taste and odor causing agents. As Scott mentioned, when chlorine dioxide was first used in the United States in 1940s at the Niagara water treatment plant, chlorine dioxide was used to control phenol-related taste and odor of the water. This is because chlorine reacts with organic contaminants in water to use chlorine substitution reaction, form odorous chlorophenol, chloramine, and this kind of organic chlorinated compounds. Chlorine dioxide, on the other hand, degrade phenols by direct oxidation to form taste and odor-free compounds. Chlorine dioxide can also very effectively oxidize hydrogen sulfide, organic sulfide compounds such as dimethyl sulfide. Reaction of chlorine dioxide with natural organic matter, surface functional groups helps to remove negative charges of colloidal particles, making their flocculation and coagulation much easier, therefore easier to remove by follow-up clarification and sedimentation process. Again, the residue of chlorine dioxide and or chlorite can prevent algae growth, filamentous fungi growth, or bacterial growth due to the disinfection effect of chlorine dioxide and or chlorite. So among common disinfectants, chlorine dioxide provides a very good removal of taste and odor and color, and with sufficient disinfectant byproduct formation information, which allows us to plan a well-established mitigation control strategies for DBPs, which Alan will present to you momentarily. Chlorine dioxide can also be applied in preventing biofouling of the RO membranes that are used in seawater desalination plants. Biofouling poses the biggest challenge in membrane fouling control. Biofilms are sticky and thick. They can create very high flow resistance. So biofilm formation usually causes irreversible damages to membrane surface and forces more frequent than usual chemical clean-in-place operation to sanitize the membrane surface from the biofilm accumulation. CIP, however, reduces the active life of the RO membrane and consumes up to 50% of desal plant operational costs. To prevent biofouling issue, chlorination is often used in pre-treatment process to disinfect the feed seawater to reduce biofilm formation. Seawater, however, has a natural content of bromide, usually around 65 to 80 ppm level. Chlorine oxidizes bromide to bromine, so essentially chlorination becomes a bromination process, which forms bromate and bromoform DBPs. Both are very tightly regulated DBPs by US EPA. Also, oftentimes, chlorination of RO membrane has been reported either ineffective in controlling biofouling or sometimes make it even worse in biofouling because of the offering of increased content of assimilable organic carbon by chlorination. Chlorine dioxide, on the other hand, can be a very effective alternative biocide to chlorination because pre-treatment with chlorine dioxide instead of chlorine can better control biofouling and eliminate bromate and bromoform DBP formation. More recent studies have shown that pure chlorine dioxide treatment had a very little impact on the membrane films in terms of water flux, salt retention, surface properties, and other RO membrane performance indicators. Chlorine dioxide treatment can have orders of magnitude longer runtime than chlorine treatment to compatible RO membranes. Another application is nitrification control. As you know, monochloramine is widely used as a secondary disinfectant in drinking water distribution systems. Chloramine use helps to maintain the total chlorine residue of distribution system and helps to control chlorinated DBP formation. However, the use of monochloramine may promote nitrification because the chloramine can decay to ammonia. Ammonia will sequentially be used by ammonia oxidizing bacteria to produce nitrite, and the nitrite is subsequently used by nitrite oxidizing bacteria to generate nitrate. Both nitrite and nitrate are regulated inorganic contaminants in drinking water with MCL at 1 ppm, 10 ppm level. Additional negative impact of nitrification include decreases pH level and alkalinity and dissolved oxygen in the distribution system. This impact on water quality increased the corrosivity of the water. Therefore, nitrification can increase the release of metal ions, including iron, manganese, lead, and copper in the finished water system. This cause potential violation in lead and copper rules, for example. Also, nitrification can cause lower disinfectant residue in the distribution system that promote bacterial regrowth. You have regrowth of total coliform and opportunistic pathogens. Using chlorine dioxide can help maintain the stability of monochloramine residue by inactivating both ammonia oxidizing bacteria and nitrite oxidizing bacteria in the distribution system. Chlorite, either as a reaction byproduct from chlorine dioxide or being directly injected as a sodium chlorite into the distribution system, helps to prevent the growth of LBs and NOBs. Chlorine dioxide use to control nitrification can also help indirectly control chlorine burn related mitigation DBPs. This kind of field application of this strategy have been successfully demonstrated in by many utilities in multiple states, including California, Texas, Kentucky, Pennsylvania, Minnesota, and so on. Okay, so next, Alan will talk with you about regulation compliance, DBP management, and chlorine dioxide generation technologies. Thank you.
Thanks, Zach. The primary reason, an oxidizer like chlorine dioxide is used is for disinfection credits. And ever since the surface treatment rule was enacted in the 1980s, 3 logs of Giardia and 4 log kill of virus is required for surface water being processed for drinking water, or any groundwater that is under the influence of surface water, which is becoming more and more common these days. And if you look at, CT values are used to determine how much of a disinfectant needs to be applied to reach the desired level of inactivation. In this table here, you can compare chlorine dioxide versus free chlorine, ozone, and monochloramine, and see that its potency is about second to that of ozone, but it also is able to have a much longer residual downstream of the application point. So that really enables it to drive to higher contact times in practice and reach higher levels of pathogen inactivation. It is also less dependent on pH, whereas free chlorine, you can see, rising from pH 7 to 9 requires about double the dosage or contact time for the same log inactivation of Giardia. But temperature is a factor in all of these disinfectants being used, with lower temperatures requiring higher dosages or contact time to attain a level of inactivation that's desired. About 10 to 15 years later, these rules were augmented with a long-term 2 enhanced surface water treatment rule, where harder to kill organisms were investigated. One such is a cryptosporidium, which is the basis of this regulation. And chlorine dioxide, ozone, and UV are the recommended methods to deal with surface water where cryptosporidium is detected and measured. Now, the level of inactivation required depends on the amount that's measured in the source waters, and a minimum of 2 disinfectants are required. This could mean UV and chlorine or chloramine. UV, chlorine dioxide, or ozone, when combined with chlorine or chloramine downstream, does have a synergistic effect, even though chlorine or chloramine alone does not adequately address cryptosporidium or these harder to kill cyst-like organisms. Cryptosporidium can cause cryptosporidiosis, which is an unpleasant gastrointestinal condition. So it's important to address these types of species and other emerging pathogens in drinking water supplies. But chlorine dioxide is not devoid of its own DBPs. As mentioned, when it is used, it is converted to the chlorite anion. About 50 to 70% of it in practice eventually converts to chlorite, along with non-halogenated but other oxidized disinfection byproducts. And it reacts with reducing agents or electron-rich organic compounds. Sunlight, UV, or stronger oxidizers can potentially convert chlorine dioxide or chlorite to chlorate ion as well. This could also arise from generator inefficiencies or impurities in the precursor chemicals. But eventually, nature does run its course with this chemistry, and chloride salt, table salt anion, is the ultimate fate of these chemistries through biological processes. Now, how can oxychlorine residuals be removed? For chlorites residuals, the predominant methods are granular activated carbon or ferrous iron salts. So such iron salts might be applied in the coagulation process downstream of chlorine dioxide application as a pre-oxidizer. Sulfide solutions can also, just like they're used for dehypoing operations, can be used to remove other oxidizers like chlorine dioxide or chlorite. But the chlorates and any potential perchlorate that arise are more persistent and harder to break down than chlorite or chlorine dioxide. Now, typically, these are not present at any reportable values, but a higher level of treatment would be required. RO membrane, UV catalyst processes, or some level of bioremediation to remove these contaminants should they exist at high levels. Now, concerning the stage 2 disinfection byproduct rules that pertain to chlorine dioxide, the primary use of chlorine dioxide, a main attribute is that it does not readily form the THMs or HAAs as discussed earlier in the talk. It also does not activate bromine and form bromate as a byproduct when bromide levels are high in the source water. So that is a main driver as to why a plant might investigate or promote the use of chlorine dioxide in their plant. But at the same time, there are regulations around the chlorite and chlorine dioxide residuals. Must be chlorite at 1 ppm, chlorine dioxide at 0.8 ppm at the effluent of the plant. And these must be monitored when using chlorine dioxide in the water treatment process. In order to stay safely below these levels, chlorine dioxide is usually only typically fed at 0.5 to 1.5 ppm as a disinfectant. In order to comply with the disinfection requirements, but also the DBP regulations, you really have to take a holistic approach and look at the plant and incorporate numerous strategies. Of course, optimization of the coagulation, sedimentation, and filtration processes can help remove all the precursors to the harmful DBBs that might arise from downstream chlorination. You can also look at where you're dosing chlorine or chlorine dioxide or other oxidizers, making sure that they have enough time to do their job to disinfect and be mostly consumed before the next process step and unit operation. Granular activated carbon is a good way to remove DBBs and precursors as well. We expect that to play a larger role in the future with the PFAS regulations. And ozone and UV can also be incorporated to reach those higher levels of disinfection, but these are really don't offer any residual downstream. So they're a good way to process water that's been cleaned up to some effect already and get a higher level of disinfection. But for DBP control, if there's still high organics coming into the chlorination stages of the plant, switching over to chlorine dioxide where you can often results in a positive decrease in what you're looking for to reach the regulatory requirements around THMs. This is some utility data from a New York system where at 4 locations after incorporating chlorine dioxide in year 2, the THM levels were greatly reduced by over 50%. Looking towards the future, we do anticipate more unit operations employed at water treatment processes to meet the higher regulations, around PFAS, but likely more DBPs in the future as well. You can see from this study, this is a good practical study from 2018 by Chu and others, where they looked at different pre-oxidation steps combined with different downstream unit operations to enhance the water quality. And the first aspect they considered was the cytotoxicity. And you can see, rotating from the top 12 o'clock position clockwise, that is, you incorporate higher levels of treatment, the water quality improves, cytotoxicity is decreased. And chlorine dioxide overall, if you look at those cases, does not have a great impact on overall cytotoxicity. But if you look at the genotoxicity, which are more of the long-term chronic health impacts, the cancer concerns of long-term exposure, what they did is they also quantitatively measured the disinfection byproducts formed and assigned a genotoxicity index rating to that water quality. And when chlorine dioxide was used as the pre-oxidant, time and time again, it showed a decrease in the overall genotoxicity. So a healthier water supply to the end user at the end of the day. Even with, when you compare the data in pink using downstream chloramination versus the data in blue chlorination, the trends were similar. And they looked at a lot of the unregulated DPBs as well, which are listed on the left-hand side here. As we know, these are not all measured and regulated at this time, but there's a good chance that some of them might be in the future. And again, this is in low bromide source water, surface water. So if bromide is present in the water supply, it would likely be even more beneficial as it does not form bromate as a byproduct. We'll briefly go through the different generation methods. So might change gears into this now. The first 4 methods here use sodium chlorite as the precursor chemistry. This is our terminology. Our 2-part chemistry uses sodium chlorite with gaseous chlorine. That has the benefit of very high purity precursors and low overall operating costs. But if you have difficulty with getting bulk chlorine on site, then the next most popular item is probably the 3-part chemistry, where liquid bleach and is combined with acid to react with sodium chlorite and convert that to chlorine dioxide. But it does require 3 chemicals, and you have to consider some degradation of the hypochlorite over time. The next 2 methods are generally for smaller scale operations, directly reacting sodium chlorite with an acid. Has a lower yield when converting the chlorite to chlorine dioxide. So a higher operating cost, but also a good purity level in the chlorine dioxide being generated. And electrochemical systems are good for smaller scale operation and have the potential to produce high purity chlorine dioxide if it is also being stripped out of the electrochemical cell. And finally, at the bottom, we have chlorate-based processes where sodium chlorate is pre-mixed with hydrogen peroxide and then activated with a 78 weight % sulfuric acid stream to drive that reaction. This is also lower cost compared to some of the other chemistry options. Minimal chloride salt byproduct, no combined chlorine gas generation, and at the end of the day, really a greener chemistry, since all sodium chlorite is produced from sodium chlorate, although there are some trace perchlorate contaminants that are likely to exist in the chlorate supply as a result of how it's produced industrially. International Dioxide provides all but the electrochemical cells for water treatment applications. The mini AC uses the AC chemistry, the acid chlorite. We have Mg2 and 3 that uses the 2-part and 3-part chemistries, which are often used in drinking water treatment. And you're able to accurately monitor the conversion efficiency in these systems. The PureDox system is also used in drinking water. And we have larger, more industrial scale systems based on 3-part chemistry that are called inline systems. They have high turndown ratios and treat more directly at the application header point. The chemicals manufactured by ERCO are ERCO Pure BCD, which are all the USA approved sodium chlorite solutions ranging from 7.5 to 31% in concentration. PureDox is the 40% chlorate precursor that can be utilized. And we have Anthium series liquid chemistry, more dilute They can be used for a number of different applications, all with EPA approvals for disinfection as well. And these are generally available in drums, totes, or bulk quantities. We also incorporate value-added services, and really for successful application of chlorine dioxide, we like to see a well thought out approach that involves a site survey to determine the best equipment design and chemical feedstocks for the application, as well as analytical training around monitoring the residuals and doing demand studies to determine the accurate doses required, as well as on-site services and engineering support to debug any issues that arise. Thank you for everyone's attendance today. If you have questions later, please be directed to our website or our general email, and we'll be sure to reconnect with you to discuss any questions in more depth.